Take any acute triangle. Now pick a point on each side and connect them to form a smaller triangle inside. Which choice gives the smallest possible perimeter? There are infinitely many options. Surely this is a nightmare to optimize. But the answer turns out to be stunning. Let's set things up. Here is our acute triangle ABC. We pick a point P on side BC, a point Q on side CA, and a point R on side AB. The inscribed triangle is PQR. We want to minimize the perimeter, PQ plus QR plus RP, over all possible positions of PQ and R. Pause and think about this. Here's a hint from physics. Imagine a laser beam bouncing off the three walls of the triangle. What path does it take? If you've studied optics, the answer should be, well, trivial. Don't worry, I'll wait. Here's the key trick. Fix P on BC. Now reflect P across side AB to get P prime, and reflect P across side AC to get P double prime. Since AB is the mirror line, AP prime equals AP. Similarly, AP double prime equals AP. So the triangle AP prime P double prime is isosceles, with the angle at A equal to 2A. Now here is the magic. Since P prime is the reflection of P across AB, the distance P prime Q equals PQ. And since P double prime is the reflection across AC, the distance RP double prime equals RP. So the perimeter PQ plus QR plus RP equals P prime Q plus QR plus RP double prime. By the triangle inequality, this is at least the straight line distance P prime P double prime. What is P prime P double prime? In the isosceles triangle with sides AP, AP, and angle 2A, the base is 2 times AP times sine of A, so the perimeter is at least 2AP sine A. To minimize, we need AP as small as possible. The shortest distance from A to side BC is the altitude, so P must be the foot of the altitude from A. Apply the same argument at each vertex. P is the foot of the altitude from A, Q from B, R from C. The minimum inscribed triangle is the orthic triangle, formed by all three altitude feet. Its perimeter works out to 4R sine A sine B sine C, where R is the circumradius. That is the answer. And here is the physicist's view. A light ray bouncing inside the triangle takes the shortest closed path when angle of incidence equals angle of reflection at each wall. That's Fermat's principle, and that path is exactly the orthic triangle. Geometry and physics giving the same beautiful answer. Follow for more elegant proofs.